So, hello everyone. Welcome to this A Spotlight. Today we are hosting Lakshmanan from Google Cloud. He'll be talking about some analysis he's done on the Google Cloud with weather forecast data and using autoencoders and embeddings. And he will show us some of the interesting results he has and also talk a bit more generally about what he does at Google and with ML and environmental prediction. So Lak has actually an interesting background. He was a research scientist for the National Severe Storms Lab in Oklahoma. And that's sort of more the academic side of weather forecasting. And then did a sabbatical at the Climate Corporation, which is a company that now mainly aims to optimize farming with respect to weather. And it's part of Bayer now, I think. But he quickly decided to then actually leave academia and move full-time to Google and works now for Google Cloud. Where he is the director of AI solutions analytics and mainly does work with clients to implement AI solutions, not necessarily related to weather, mostly not related to weather, but sometimes he still finds time to play with weather data. And so, yeah, I'll hand it over to Lak now to start with this presentation. Thanks.
Thank you, Andre. As Andre said, I'm Lak. I lead analytics and AI solutions at Google Cloud. And today I want to talk to you about how to create image embeddings for weather forecast images. Embeddings are this thing that's becoming extremely popular and extremely common in a variety of different users of ML. And so I got curious a few months ago about whether they would work in weather forecast too. And so this is basically, it turns out, long story short, that they are. And you can actually use them for searching for analogs, for doing interpolation for things like nowcasting, and for clustering different types of weather scenarios. So, but I'll kind of step back a little bit and say, why am I at Google? Why am I talking about weather forecasts? Then talk about what are embeddings, and then explain the weather forecast images that I'm using, and like how do they come about, and then like delve into how to create those embeddings, and finally about how these embeddings have some nice properties that open up a variety of different use cases in weather. So even if you're not meteorologists, I hope that I will inspire you into looking at embeddings for a variety of different other use cases. Okay. So first of all, like why am I talking about weather forecasts? Well, at Google, right, we do a lot of things that are adjacent to weather. So for example, Google Search, Google Maps, Android, we basically do these public alerts, and public alerts from Google have been sent to over 2 billion people, hundreds of thousands of events. And as you can imagine, this is a great way for public sector agencies to communicate emergency messages. It used to be that you had like radio, for example, but radio, people tend to listen to it only when they're commuting. So we need some way of communicating with people on devices that they always have with them, and these days that's mobile phones. And so the public alerts are an incredibly useful way to keep the public safe. But it's not just about taking the public alerts and providing them. We also do quite a bit of research in what we call the AI for good area. So for example, this is work that we did in India on doing flood forecasting. And what you see on the left is what the flood forecast and the corresponding evacuation would have been using public sources. And what you see on the right is what the flood forecast and the corresponding evacuation area would be using Google models. So the Google models are the models of inundation, right? And higher resolution DEM maps, and better like flow forecasting. And as you can see, like each of these dark dots are people, and having a more accurate model basically means that you have to evacuate fewer people. The roads are less blocked. It's much more likely that the people that the emergency managers need to evacuate actually are able to leave the area. So this is and again an incredibly useful kind of thing. And now we can combine the two. So we have the research of basically building better flood forecasts and being able to basically provide that flood forecast in mobile apps. So for example, this is basically what the live system looks like. This is the Brahmaputra Basin, and working with the Indian Meteorological Department to help provide flood forecasts. Okay. And of course, because it's machine learning, we also look at like how does this do better than what you would do earlier, and we measure precision, we measure recall, and it's as that demo showed, we kind of think what they are. So we have active research at a variety of different groups in Google that look at improving various areas of the weather forecasting process. In fact, we had a really cool paper a few months ago on doing nowcasting using the HER, where we're able to basically do weather forecasts up to about 8 hours. And this is, again, pretty revolutionary because to date, most nowcasts, statistical forecasts using weather data usually goes only up to an hour, hour and a half. But this was able to go up to 8 hours. But one of the criticisms was that it was blurry. And just last week, there was a new paper out of DeepMind, which is part of Google, looking at how to, and working with the UK Met Department in this case, on how to basically create forecasts where the images are much more realistic. And this is using what are called generational GANs, right? Generative models. So there's a lot of work in terms of all of the neat stuff that happens in ML research and the application of it to various scientific domains, including weather forecasts. So, but in this talk, I'm going to be talking about embeddings and how they can be useful. So let's talk about what exactly are embeddings. And embeddings come from this original, for example, let's take problem of recommending movies to customers. This is what YouTube does, right? You basically have, let's say, 500,000 movies. You have 10 million customers, and you need to basically recommend movies to them. The way you do this is that every customer has seen a few of the movies and have rated them. And based on this, you need to fill out this entire matrix, and you need to know what would this customer rate this movie if they were to see it. One approach is that you can say, well, let's go ahead and look at the average age of the viewers for each movie, and then we just basically rank them where Shrek is oriented towards really young viewers, and Memento and Dark Knight Rises are towards really much older, more adult audiences, right? That's one dimension. And then based on that, we might say, well, this is how we recommend movies to you. As you can imagine, that by itself is not going to be great. Well, you could maybe use a second dimension where you say, let's look at the gross ticket sales of the movie, right? Where Shrek sells a lot and Memento is like an art house movie. And you have another dimension. And then you can basically put these two things together to basically say, if this person is interested in art house movies and they are young, then maybe we should basically recommend to them Triplets of Belleville or something like that, right? So we could do something like that. And as you can think, you can keep adding these features. And so every input, movie and user, might have like n dimensions. And you might basically say all of this information, we're going to basically reduce it down to a smaller set of things, like the age, like how often is a movie watched, etc. That dimensionality reduction is what embeddings are about. So, if you're from a statistical background, what a PCA does is exactly what embeddings do. except that this reduction can be through a neural network. So it can be non-linear. So you have all the information that you have about any particular topic, and you pass it through a deep learning model, and you reduce it not to a classification result or a regression result, but to a vector representation. And that vector representation is what we call an embedding, right? So in this case, we have a two-dimensional embedding, and these two axes actually have names, but the names themselves are like the human way of doing things. And you could imagine that you can learn this thing automatically from data. So the coordinates, it's a vector representation, and you can learn this from the data. How do you learn this from the data? How do you take a movie ID, which is like this one hot encoded string, and convert that movie ID into an embedding layer consisting of 4 latent factors? We need to have some kind of learnable way to do that. And the way that you typically do it is that you solve a classification problem, right? Let's say, for example, we want to basically take all of the words in a real estate ad, and we want to basically take that words and do dimensionality reduction of them and create a 3-dimensional embedding. One way to do this is to take the words in the real estate ad, the number of rooms, number of beds, etc., that we would do, and use it to predict the price of the house. And once we create this model, as you can see, all the information in the words in the real estate ad are passed through this one layer that has 3 nodes in it. And that essentially means that we're now representing this really, this really information-rich thing with these 3 numbers, and that's your dimensionality reduction. And you can basically do this with a deep learning model, right? So that's the basic idea. You train a normal regression or classification model, but you take this thing that you want to do dimensionality reduction on, and you pass it through a very narrow layer, and that basically forces the model to learn the most concise representation of this information relevant to this problem. In this case, the words in the real estate ad that affect the price of the house. The model is going to learn to ignore all the other information, like the words like the and a and how, but instead learn to basically focus on words like granite and large and spacious and airy and light-filled, all of these things that basically reflect the price of the house, right? So that's essentially the idea here about how do you create an embedding layer. And these embeddings, of course, they provide that dimensionality reduction, okay? And you can use this with pixels of data, you can use it with words, you can do whatever you want, okay? So that's what embeddings are. Now, what I want to talk about is how to create embeddings of weather forecast images, okay? So the data that I'm going to be taking is of the high-resolution rapid refresh model. It's called a HER, right? When you hear me say a HER, that's basically what I'm talking about. It is a 3-kilometer resolution, right? So in the world of weather models, this is relatively high resolution for a continental scale model, right? So obviously you can have 50-meter resolution models on a tiny on a tornado. People do 50-meter resolution models, but that's not what we're talking about. We're talking about continental scale. We're talking about the entire US, right? And basically creating a 3-kilometer resolution model is a pretty high resolution model. So that's why it's high resolution. It's rapid refresh. Normally weather models basically come about once a day, right? Or maybe maximum twice a day. The HER comes about every hour, right? And so you basically have much more frequent updates. And the basic thing that I'm going to do is I'm going to take the HER data. This is an image, and there's a bunch of different fields, because numerical models have a bunch of different fields in it. The particular field that I'm going to take is a composite reflectivity, which is basically it simulates what the radar image would look like. And it's a very, very understandable thing. Everyone has seen it on TV, etc. So you look at a radar image and you think that rainstorms look like that, but they don't look like that. But it's a pretty good representation of where the rain is, where the hail is, etc. So that's what we want to represent. So the way the HER does things is that it takes the observations. That's the stuff on the left. So there's, in the US, there's like 150 radar. In Canada, you basically have, they're called C-band radar in Canada. So it's like, it's a different type of radar, but you do have radar coverage over much of southern Canada. So you basically have these radar images, and these are then composited and basically assimilated. Assimilation meaning what you do is that you take the radar data and you basically fit it into the numerical physical equations of the model. So that's what's called the analysis field. And that's basically the thing that I'm going to be doing a dimensionality reduction on. Okay. Now, I need to basically get data, right? If I want to train a deep learning model, I need lots and lots and lots of data. Where do I get data from? It's a big problem in a lot of fields like weather, is how do I get the kind of data that I need to train ML models on? And this is where the cloud comes in. Okay, so all the HER data is available on Google Cloud and Google Cloud Storage. And so you don't need to download any of this data. You can just spin up a machine and read it, right? So basically, if you go to that link, for example, you will basically be able to look at real-time HER data that is being basically streaming in, okay? And what I'm going to be doing is that I'm going to be reading the analysis grids, 0, 0, which is the analysis grids that are produced every hour. So the HER data, unfortunately, is distributed on what are called GRIB files. And this is, again, a very common problem in science, I think, is that our data formats were decided years and years ago when we were not really thinking about being able to read data on the fly. Remember what I said, right? I want to basically go get a machine and read this data on the fly. Because when I'm doing my TensorFlow training, I want to basically spin up a bunch of GPUs and have them read it in parallel. And in order to do that, I need to take that HER data and I need to basically reformat it, okay? Because I don't want all of the data in the GRIB file. I want only the reflectivity data. The GRIB reading library can only read local files, and the latency is going to be pretty unacceptable. It's not really set up for doing ML. So if you want to do ML, there's now new efforts in the weather field. There's a new format called ZAR, which helps address this problem where you can read slices of data on the fly. Okay, but okay, I'm not going to use ZAR. I know exactly what I want to do. I want to do ML. So I'll basically go ahead and take it from GRIB all the way into TensorFlow records. TensorFlow records are going to give me a really efficient way to read this data and train ML models as batches. So what I'm going to do is I'm basically going to use the GRIB data file, right? That's basically what that file looks like. And I'm going to basically read it. And having read that using a library called X-ray, I'll convert it into a TensorFlow record where it just has the pixel values. That's all I care about. So I'll basically write out a 2D array of pixel values that are appropriately scaled and ready for basically feeding into an ML model. So what I now get is sharded files of TensorFlow records, okay, where each file contains maybe about 20 images in it. And I have like many of these files, and each of these is just the pixel values. So they just have a 1059 by 1799 image, and this image basically contains the reflectivity data. Okay, so that's now I've now have my data set. I'm ready to go create the embeddings. So how do I create embeddings from images? Okay, so remember, to create embeddings, we need a learning task. We need to train an ML model. So in the case of houses, we said we're going to train a model to go predict the price of the house. If we were to have MNIST, we might say, okay, I'm going to take the MNIST image and predict what digit is there in the image. What kind of a learning task can I do on the HER images? The problem is I don't want to go through that entire years worth of her data every hour and label it, give it some kind of a true answer. I need a way to train an embedding. I need a learning task that doesn't involve me going and labeling everything. What can I do? Right. So thing is, I need an auxiliary learning task. I should do it without labeling, because if I don't have to label, I can use all of the data available. So as the inspiration, take, for example, how word embeddings are created, right? We want to basically take words and we want to basically figure out a representation for them. And we could have done what we did in the real estate ad and trained it to predict a house, but that's going to be only relevant for real estate and houses. I want a representation for words that's more general. So what do? Well, what Google did was that we went and digitized books. So you basically have a sentence, the cat sits on the mat, and you say, given the words the cat sits on the, predict the word mat. Now, this is an already existing data set because we have tons of books out there, tons of articles, and we can basically train an ML model to predict the next word in a sentence. And by training the model to predict the next word in the sentence, we basically learn how to represent words, going from one hot encoding the words, which is basically English has like 100,000 words. It's going to be a terribly sparse representation to something very dense and something very nice. So we can basically do autoencoders for images. The basic idea is you take an image, you pass it through a network, you get it really, really, really narrow, and then you pass it back out to something, try to get back the original reconstructed image. The image serves as its own label. And as you can see from the diagram, we have learned to represent this image with just 2 latent numbers. That's the basic idea. So for the her, this is basically what I'm going to do. I'm going to take the reflectivity input. I'm going to crop it to be a 2-power number, so 1024 by 1792, and then basically pass it through a series of convolutional layers until I get to an embedding, which is just 50 numbers. So now I've gotten 50 numbers. Then the decoder takes those 50 numbers and passes it through a bunch of upsampling layers and returns back the reconstructed data. So that's the basic idea behind my embeddings. Now, how many layers do I need, right? Well, I don't know. So what I'll do is I will basically take 4 images of really small batch and hyperparameter tune this to get the lowest possible loss. And this will, I can now create an architecture that is capable of adequately representing all the information content in a her image, right? And it turns out that if I have 4 filters with a pool size of 4 and 4 layers, it is able to get the lowest possible loss. So that's the hyperparameters that I picked. And having done that, I now threw this hyperparameter thing on 1 year of data by saying, here's the input, go get all the TensorFlow records corresponding to 2019. Okay, so train that whole thing, and I now get a embedding. The embedding is 15 numbers long, right? So what I now have is an embedding. The question is, does this embedding have the nice properties that we would want in an embedding? What are the nice properties that you want in an embedding? Well, suppose you have an embedding and you've created an embedding of the MNIST images, right? The digitized images, 0s, 1, 2, 3, etc. It turns out that the embeddings of all the 1s clustered together, all the 0s clustered together, all the 2s clustered together, all the 5s clustered there, the 9s and the 4s. And this is kind of interesting, right? 4, 9, right? 4 and 9 are very similar to each other. There's just this one thing at the one stroke at the top that are different. Whereas a 4 and a 1 are very far away from each other because they're very different from each other. That's what we want in an embedding. Similar items have to be similar to each other, and vector dimensions must have meaning. What I mean by vector dimensions have meaning. For example, if you take a word embedding, you look at man and you look at woman, you subtract the two vector numbers, you take that difference and you add it to king, and you will get queen. Okay, so those vector dimensions have meaning. That's what we want in a good embedding. Now we've created an embedding on the her data. Does it behave this nicely? Okay. So why is this important? Because you can use this for a variety of different uses. For example, the way that you do embeddings on audio is how you get amazing recommendations out of Spotify, right? So what happens is you take a song and you represent an embedding and you find similar embeddings. So it doesn't have to have the same genre. If it has the same sound, it will turn up. So I listen to this Indian music called Carnatic music, and it's always funny that Spotify will actually pick jazz songs that basically have a Carnatic raga to them. And it's pretty interesting that it's able to figure that out. The completely different genres, these two singers and artists will never have even heard of each other, but the songs actually sound similar. And because the sound is similar, it's able to basically surface that up as recommendations. Okay. So how, in the case of a her, how does that look like? So you basically have an image, and you basically taking the encoder and saying predict it. And this is basically what that embedding looks like if I were to take that embedding and pass it back to the decoder. So this is the reconstructed image. It is a sort of blurry version of the original data. I mean, that's what dimensionality reduction does for an image. It basically recreates the image, but sort of in a compressed way. Okay? But the embeddings, we can check if they capture a closeness relationship. What can I do? I can basically take a particular embedding of a particular timestamp and say, what are all the ones that are close to this? And I just do a search on the entire 2019 data, and lo and behold, the ones that are closest to 5 o'clock is 6 o'clock and 4 o'clock, then 7 o'clock and 3 o'clock. Makes perfect sense. What images are the closest to a particular timestamp? It's the ones that are an hour apart from each other. Okay? This kind of gives us this confidence that this embedding is capturing a closeness relationship. Now, this is not very useful. What if I remove the images from plus or minus 1 day and I do the same search? Okay. Now, on this 1 year of data, if I were to look for images that are close to this, I get these two, right? Basically, right, I get images that seem to have storms in the similar parts of the country, which is, again, pretty nice. Or, and this is really interesting, I get images that have similar kinds of storms in a different part of the country. That's amazing, right? Okay, so so you notice that basically all these three are linear storms in different parts, and then you basically have all of them have storms in the southwest part, right? So there's some location component. There's also some storm morphology component. Okay, so that's the thing that embeddings give you, this closeness relationship that is super, super relevant. So this means that we can actually use embeddings to search for case studies. And there's a way to efficiently search embedding vectors to find things that are similar to each other. The other thing that you can do is that if I take an image at T1 and an image at T-1, and I average the two, do I get an image that is similar to T0? That's a very simple test. And if it does, then that means that I can use embeddings to find what the images would have looked like all the way in between these two timestamps. Even though the her is produced only once an hour, I can now use it to find the appropriate ways to interpolate and take account storm movement, etc., to find the times in between. And long story short, yes, it works. And the differential between the average here and this one is much smaller than this difference or this difference. So that tells us that interpolation with embeddings also works. The third thing that we can do is that we can take these embedding vectors, which are just a vector, it's a 50-dimensional number, and cluster it into 5 clusters. So that's what I'm doing. I'm taking on my embeddings. I'm basically saying, go ahead and do k-means clustering on it with 5 clusters. And when I get that, I get 5 centroids. We can now plot those 5 centroids. And this is what those 5 centroids look like. So first centroid consists of a lot of storms in the Midwest. Second centroid, right, consists of this kind of a squall line marching through, right? Another centroid consists of a lot of weather in the Cleveland, New York corridor and a storm, right? The interesting thing to me living in Seattle is that all 5 of these centroids involve it raining in Seattle. And with that, I will take questions. Okay. And here are some links here, right? To basically find all of the code for everything that I've talked about is on GitHub. Okay, there's articles on how to convert the her data into TensorFlow records, how to use autoencoders to create embeddings. Okay, so you can just find that from that link. Okay, and shameless plugs. Okay, 3 books. A lot of the SQL statements that I showed you, for example, this one is k-means clustering. It's in this technology called BigQuery. So this is a way to basically simplify a lot of ML that we do on structured data, right? You wouldn't do it for images, but for anything structured. So you can do machine learning, you can do data analytics, etc. So that's the first book here, BigQuery. Data science and Google Cloud Platform is about how to do all kinds of data science, everything from ingesting data. Okay, sorry, looks like Amber Alerts. Sorry. Okay, and the third one is one of the recent book that came out early this year called Machine Learning Design Patterns. Embeddings are one of those design patterns that we discuss in the book. With that, I will take questions.
Okay, thank you very much, Lak. That was a very interesting presentation. And so you mentioned you have a GitHub repo for this, right?
Yes, so you can get at the GitHub repo by going to that link or doing a Google search for the title of this particular title.
Is that set up to run on the Google Cloud, or is there something that one could run locally, or just?
Basically, this is all TensorFlow code, right? So what is it? Compression, search, interpolations,
yeah,
on weather forecast images. There we go. There is that. And scroll down to the GitHub repository. There it is. And this particular thing is just it's a notebook, and you will have to basically get the data. Unfortunately, this data is on Google Cloud. So to try this thing, it is much easier to do it on Google. But of course, this is public data, so you can download it and try it out locally if you want.
Mm-hmm. Yeah, so you can download the weather data also from NSAP, from the National Center for Environmental Prediction.
Exactly. These are the grip. It starts with the grip files. So download them from NSAP, and after that, it is all just TensorFlow code. So you can try this whole thing.
NSAP just runs an FTP server. That's right. Okay, so yeah, we do have a question. Can these embeddings be used in some way for prediction?
Can embeddings be used for predictions? Embeddings are a way of representing information, right? So what you're now asking is, can the current image be used for predicting the future? And the answer is yes. That's what nowcasting is. If you have a series of current images, you do a statistical forecast of the future. Okay, but you wouldn't go through embeddings for that, right? The embeddings will fall out naturally, because remember that when I create the embeddings, I said take the current data and predict the same image. Why do that? Take the current image and provide the next image. Right? So embeddings are a way to basically come up with the intermediate stuff, but you don't need to go through an embedding to predict the future. You would go with the raw data and directly use it to predict the future.
So is that what he mentioned? That was a Google effort to do nowcasting,
Right.
also
Yeah.
in the her
So
context.
that is her. Let me just see if I can find it. Precipitation nowcast.
So just a note on this her system. So this is basically like the leading short-term weather forecast system.
Correct. So this is the one I was talking about, a neural weather model for 8-hour precipitation forecasting.
Okay.
And this is basically doing that forecast, and that's exactly what it's doing. It's basically taking the current set of images and using them to basically predict the future.
And you're only using the radar reflectivity, or are you also using other data from?
No, this is just purely image forecast. It's not using any other metadata. It's just.
So you're not looking even at the winds or anything. You're just looking at the rain displacement.
We're not looking at the observations or anything at all. We're just looking at the current set of images and predicting it. It's a pure, complete nowcasting problem.
Okay, very interesting. Okay, so I would have a question from a more technical point of view. So how sensitive? So in metrology, there's a lot of debate about skill scores, and that RMSE is not a good skill score. And so, what do you use as your loss function?
The loss function, because you're training
it's sort of similar to the skill score, right?
You tend to use the similar loss functions that you use everywhere else. So in this case, we actually cast the problem as a classification problem, because we end up basically predicting which bin of the precipitation value it's going to be. And then we use cross entropy to train the ML model. Okay. The metric that we use to evaluate the model, we do a variety of them. And in fact, like the DeepMind paper that I was talking about, essentially goes ahead and does regional evaluations. It does the probability comparisons at different levels. It does a whole variety of them. Okay, but that's the evaluation bit. When you train the ML model, you train with cross entropy.
Okay. Okay. So another question from the chat is, can you sort of talk a bit more about the background of Google getting into flood forecasting and weather forecasting?
I wouldn't say Google getting into it. It's like, so we have this group called Google Accelerated Science. So we work with a lot of the scientific organizations and collaborate with them. So for example, the DeepMind paper was in collaboration with the UK Met Office. The flood forecasting initiative was in collaboration with the Indian Meteorological Bureau. The assimilation work that we're doing is in collaboration with NOAA. So this is where Google's bringing our expertise in AI and now all of the AI research, and collaborating with industry leaders. And the industry leaders would be the like NOAA, IMD, UK Met Office, etc., to basically advance the state of the art there. So that's very similar to how like DeepMind worked with biologists on protein folding, right? It's not like DeepMind did the work, but DeepMind in collaboration with the industry teams to basically advance the state of the art in a particular domain.
Okay, so that's interesting. And so, what is Google's sort of view on sort of predictive modeling? So, in weather forecasting, we use physical modeling a lot, and basically, we've always done sort of predictive analytics, if you will. And
yeah, so absolutely right. I don't think it's an either or. There's the weather forecasting process consists of a lot of different things. That's why I said, for example, we're trying to use machine learning for post-processing, which people have done for a long time, but nobody's in machine learning for assimilation. And we're trying to use machine learning for data assimilation. It'll still be the same physical forecast model that you end up using, but wouldn't it be nicer if you got a much better assimilated system? Or like what you're doing here with the HER, wouldn't it be nice if we got a much faster, like because in machine learning forecast, we can get in 2 seconds, whereas running an ML model takes hours. So wouldn't it be nice to basically do
a weather model, right?
Like ML, numerical weather model takes hours. So wouldn't it be nice to use a ML model to get more frequent updates to what the physical model does? So there's ways in which we can apply ML to improve. So it's not an either or. We're not trying to replace the numerical model in any way, because that doesn't work, right? We want to keep the physical equations. However, we can still improve the way that they get employed, and that's basically where much of this comes in.
That's right. And have you thought about working on some of the parameterizations in the models as well?
Not at present. I don't know about anyone currently doing the parameterizations, but that's, again, there's a lot of really cool work out of a lot of different, now, I'm part of the American Meteorological Society AI committee, and 10 years ago, we used to get about 30, 40 papers to the conference. And last year we had about 500 papers in the conference, right? So this whole field is exploding in terms of how much machine learning is getting applied to various parts of the weather enterprise. So I don't think at this point I know anymore what all people are doing. So for all I know, there may be somebody out there already working on this problem of parameterization.
There have been like 3 papers maybe so far on collection parameterization, I think.
Okay.
Which is pretty interesting.
I see. Cool.
Yeah. Okay, so I didn't see any more questions in the chat. Do you have any closing words, or I guess?
No, that's pretty much. I really enjoyed this, and thank you all very much.
Yeah, thank you very much for the presentation. It's really cool to learn what Google is doing up there in this area, and how to apply machine learning to these kind of data. And there is a lot of data from these weather models. The output is just a ton of data, and you can actually get it on most major cloud providers, as far as I know, and also from NSAP, but on an FTP server. So with that, I think we'll close. Thank you very much, Lak.
You're welcome.
That was an excellent presentation.
Bye.
See you all next time.